The last logarithmic rule we have is a little bit different from the others. It's not as commonly used, but it is what we call a change of base formula. Um, if you recall, talking about trying to solve some of the equations, like you might get something along the lines of like x equals log base 3 of 11. And then you're kind of just like, cool, what is that? I don't know, 3 squared is 9. It's bigger than 2. But like, how do we go from there? Your calculator has got the ln and the log, so the base e and the base 10 buttons. But they don't have all the possible bases because it's any real number. Your calculator does not have infinitely many buttons to it. Some graphing calculators do have an option to set up your base logarithms, but I would never recommend buying a graphing calculator because they're crazy expensive and you're never allowed to use them in university. So what we can use instead is what's called a change of base formula. And so what you can see, if we have any logarithm log base b of a, what we can actually do is rewrite it on the right here as a base c logarithm, or actually as a quotient of base c logarithms. So we take the a and we put it inside the top logarithm, and then the b goes inside the bottom logarithm. And yes, we get log base c of a divided by log base c of b. And we can actually do that. This statement is actually going to be true for any c. It doesn't matter. You could choose c equals e, c equals 10, or c equals 135. It absolutely doesn't matter. And that's the nice part of it, because we can actually just take anything and rewrite it with ln or log. So I'm just going to do an explanation of where this equation comes from, why it's true. It's a little different than the other explanations. I have to do a bit of a different trick to this. So what I'm going to do is let x equal log base b of a. Now what I'm going to do is rewrite this as an exponential. And so that means that b to the x equals a. So that's the equivalent exponential form. Now what I'm going to do is something kind of bizarre. I'm going to do log base c of both sides. So I'm going to have log base c of b to the x equals log base c of a. And then my power rule is actually going to allow me to pull that x to the front, and then maybe you can see where this is going now. I've got x log base c of b is log base c of a, and that's basically it. X is log, oh sorry, that's a loc, not a log. Log c of a divided by log c of b. So this is a formula that just kind of does that for you. What you'll find when you're actually equation solving, though, is that you'll probably actually just on this step, this initial step, yeah, that middle step there, you're just going to use ln, and then you don't need to do any change of base. You'll just do ln and then use that, maybe that power rule, to help you get to the last step. So if you don't know this change of base formula, it's really not going to hurt you in any measurable way too much, aside from like questions on the assignment. So I wouldn't worry about it for the future, though. All right, so we'll use this formula in action here, and we're going to evaluate a couple of these logarithms. So we'll do it to 3 decimal places. So log base 3 to the 11. So what I can do, I'm just going to use ln. You can do it with base 10 log, and you should find that you get the exact same answer. But I'm going to use ln. So I'm going to use c equals e to write with the ln functions. And so according to the formula, what I should get is ln of the a, the input, divided by ln of the b, so the base. So I'd get ln 11 divided by ln 3. I do strongly recommend doing this all in one calculation in your calculator, because I have mentioned before, rounding errors are a really big issue with exponentials. So I'm actually just going to punch in ln 11 divided by ln 3. And what I'm getting here is If I round it to 3 decimal places, 2.183. Okay. So if you want to check the number that I've gotten here, if I have x equals log base 3 of 11, that means that x is the number, so that 3 to the x equals 11. And so what I'm going to do is check what 3 to the 2.183 is. So we know that x should be a little bit bigger than 2 because 3 squared is 9. So this seems at least reasonable. 3 to the 2.183 is 11.004. And then some decimals after. So that's pretty good. This is good. I'll try the same thing on the next one. So I'm going to get log base 10 of 0.0012. Same idea. I'm going to turn this into ln. It'll be ln of the higher, like the raised number, 0.123, divided by ln of 10. I could have also, okay. Actually, you know what? This is a good one to check. I wasn't even paying attention. I could have totally just done this with the log button. So maybe I'll do that as a check after, just to make sure we do get the same number. But yeah, so we can evaluate this. Ln of 0.0123 divided by ln 10. And I'm getting, when I punch that in, negative 1.910, my 3 decimal places. I can also check. I can do 2 checks on this because I did a log base 10. So if I did log of 0.0123, and I would get hopefully the same thing. Yeah, I get the same thing, which is good. Negative 1.910, good. Or I can do another check. 10 to the power of negative 1.910 is 0.01230 ... There's like a 2 and then some other decimals after that. So it's looking pretty good. This formula seems to work. And so, yeah, we can use this now to, specifically to know what the solutions to some of the past equations that we haven't been able to tackle yet are. So it's just a good formula for making things what you would call calculator ready. So calculator ready just means like it's written in ln or log because we can just punch it in the way it's read, essentially. Whereas like log base 311, that's not calculator ready because we don't have a button for that. So it just helps us get numbers, essentially.